Welcome back to the second part of this presentation. Alright, let's get on to the third question. Alright, determine the maximum amount of water that needs to be added to the mix and provide the final batching quantity per meter cube. This is the maximum amount of water to ensure that we don't exceed the water cement ratio of 0.55. Alright, the total water required by the mix is 141.94 liters, and we obtained that from the previous presentation, so I highly recommend you to go back and watch it. The water in the aggregates, the sand plus the coarse aggregate, was 26.88 plus 26.33, which gave us a total of 53.21 liters, okay, or kilogram per meter cube. Alright, therefore the maximum net water to be added is 141.94 minus 53.21, and that will be 88.72 liters. Now the final batching quantity per meter cubed, I've tabulated it here. We have the materials and the quantity as in kilogram per meter cubed. Alright, the cement, the dry components only, you'll find it as 258.06. I've written it all out here for you to see it. And if you note that we have now documented sand, wet to dry, so we've included the 4% moisture, as well as the coarse aggregate. We've included the 2% moisture. All right, and at the end here, we have the net water to add, which is 88.72 liters. Now, to check the total weight, if we add all of this together, we will get the normal density that we started off with, which is 2400 kilogram per meter cubed. And this is how we do a quick check. And we know that we are going on the right track. All right, the final question, number 4, the fourth one. Let's determine the batching quantity required to make up the concrete mix for the entire slab on ground, and we will document the answer in kilogram. Okay, we first need to work out the volume of the entire slab, and we will do this slowly so that we don't miss anything. Let's start off with the top shell of a 100 millimeter slab, this whole entire area here. Okay, what do we have? We have the total length is 16,000 millimeters, and we have a rebate with each side, which is 150 millimeters. Therefore, the effective slab length in the long direction is 16,000 minus 300, and that will give us 15,700 millimeters. So we've taken both rebates, 2 times 150, and that's why it's 300. Huh? The total length in the shorter direction is 8,000, and the rebate width is exactly the same, 150 millimeters. Therefore, the effective slab length in the shorter direction is 8,000 minus 300, and that will be 7,700 millimeters. The slab shell volume in meter cubed will be 15.7. We convert everything into meters, so 15.7 multiplied by 7.7, the shorter direction, multiplied by the height, which is 0.1, and that will be 12.089 meter cubed. And generally, the slab shell gives us the most volume in respect to the entire slab, that we get the most amount of volume out of that. All right, the internal stiffening beams, IB1, IB2, and IB3. Look, it is always good to number them so that we don't make any mistakes in our calculations. Now these hatched areas here. The total length in the shorter direction is 8,000, and the width of the edge beams is 450 either sides, or both sides, I mean. Therefore, the effective internal beam length in that shorter direction is 8,000 minus 900, and that will be 7,100 millimeters. The width of the internal beams are constant throughout the whole slab, which is 300 millimeters, and the height is 400 in this case. We don't take the 100 millimeter slab thickness because we have taken it in the previous calculation. So the height here is 400 millimeters. Therefore, one internal beam in that shorter direction is 7.1 times 0.3 times 0.4, and that will be 0.852 meter cubed. The total volume of the three beams will be 3 times 0.852, and that will give us 2.556 meter cubed. Now, the internal stiffening beam IB4. This whole long beam here, which we have broken up into these hatched areas here. All right. Now, for this beam, we need to remember to take away the three little areas of that internal beam here, because we have already taken it in the previous calculation with that shorter direction. All right. Therefore, the total length in the long direction is 16,000, and the width of the edge beams are 450 either side. Therefore, so we have 900 millimeters, so 3 times, and we also take the width of the internal beams, which is 300 multiplied by 3, and that is 900. So then the effective internal beam length in that long direction will be 16,000 minus 900 to cater for the edge beams, minus another 900 to cater for the 3 internal beams, and that will be 14,200 millimeters. Again, the width of the internal beams, that it's still 300 millimeters, and the height is 400. Therefore, the volume of IB4 will be 14.2 times 0.3 times 0.4, and that will be 1.704 meter cubed. And again, because we have one beam, so that will be 1 times 1.704. Okay, what else? We have the external edge beams. Now let's start with EB3 and EB4, this hatched area here. All right, the total length of EB3 and EB4 is 8,000, and the width of the edge beams is 450 either ends. Okay, therefore the effective external beam length in that shorter direction is 8,000 minus 900, and it's 7,100 millimeters. The width of the edge beam is 450, and the height is 400 millimeters. Now remember that this height that we call 400 millimeters is just to calculate the volume. But technically, when we say the design, and when we design the edge beam, the depth of the edge beam must be below top of slab. Okay, so when we're designing the edge beams for moment, for shear, for torsion, we take the depth of 500 millimeters. But to calculate the volume in this case, we say 400 millimeters. Okay, so volume of one edge beam will be 7.1 times the width 450, 0.45 times the height of 0.4, and that will be 1.278 meter cubed. And the total volume of the external beams in that shorter direction will be 2 times 1.278, and that will be 2.556 meter cubed. Almost there. Now to the two external edge beams, EB1 and EB2. All right, this hatched area right over here. Again, the total length of EB1 and EB2 in the longer direction is 16,000 millimeters. And this time, we don't need to take away the two 450 edge beams, okay? Because we've included that. So the effective external beam length in the larger direction is 16,000 millimeters. The width of the edge beam is 450. And the height again stays as 400. So the volume of one edge beam is 16 multiplied by 0.45 by 0.4, and that will be 2.88 meter cubed. The total volume of the external beams in the long direction is 2 times 2.88, and that will be 5.76. All right, now the total volume of the slab on ground, again we tabulate everything and we number them. so that even if we want to do it on Excel later on, it will be easy for us to keep track of all of these figures. All right, we have the slab, which is the slab shell, and the corresponding volume, IB1, IB2, and IB3, IB4, and the edge beams. If we add all of this up, we will get a volume of 24.66 meter cubed. The final batching quantities for the entire slab in kilogram, what we do, we simply get the previous densities that we calculated and multiply it by the total volume we found out. So for cement, 258.06 times 24.66. So we multiply everything by the volume that we have calculated. And even at the end as well, the net water to add for the entire slab will be 2,187.83 kilogram, or liters, okay? So that's the total weight. Now, if you add everything together, all the materials together, we will end up getting about 59,183.89 kilogram. Very heavy. We convert everything into kilonewton, we'll get about 580 kilonewton. So yeah, working out the volume of the slab and the weight of each material would kind of help us determine many things. We can go out and then calculate the bearing capacity and the bearing stress on the slab. The bearing stress on the soil due to the dead load of the slab. We could also work out the costing of the concrete materials alone. Yeah, so how much is concrete these days? I know here in Australia, particularly Victoria, we might be paying somewhere between $300 and maybe $400 per meter cubed. So for 20 MPa, you'd be looking at 350 at least per meter cubed. And the interesting thing is, if you jump up to 32 and 40 MPa, the price difference is not that much, and I've noticed that. You can get only an increase of maybe $50 to $80 per meter cubed. Very interesting, because probably part of designing, I would rather go up in strength, but then workability might be an issue as well. So yeah. So in this example, if we have 20 MPa concrete and the volume of 24.66 meter cube, and let's say a 10% material wastage. So you're looking at, 27.1 kilogram per meter cube. And if we assume, say, $350 per kilogram, kilogram per meter cube of concrete, then you're looking at, you're looking probably, I'll just look it up and type it out. So that's 350. Yeah, so you're looking at $9,500 just for the concrete materials alone. And this is not including reinforcements and labor as well. And it's not including excavation cost. So yeah, I miss the good old days where we used to pay $90 to $100 per meter cube of concrete for 20 MPa. So yeah. Wow, okay, so this wraps up our long discussion about this topic. If you have enjoyed this video, please share, like, and subscribe so that others may also learn. Until next time, we hope that you have a great afternoon.